that. And yeah, welcome to the MDP review session. Yeah, let's get started. So I'll do a semi-brief overview of MDPs and the ways we solve them, and then we have 3 problems prepared on this worksheet. So let me see if I can turn off the bell thing. That's fine. Okay, so at a high level, MDPs are there to model a non-deterministic world. And they consist of states, actions, a discount factor, a transition probability function, and a reward function. As a reminder, this transition probability function is basically saying, like, what's the probability that you get to state S prime, given that you start in state S and A. And this reward function is just telling you, like, what reward will you get if you start S, take action A, and transition to S prime. So what are some quantities that we care about? Well, one thing that we care about is the value of a state. And the way we define value is the expected discounted sum of rewards if you start S and you act optimally thereafter. So yeah, that's value. And the star just means optimal value. We also define this thing called Q value. That's sort of like one step removed from value, where we say Q value, expected discounted sum of rewards, if you first take action A and then act optimally thereafter. And the reason this is useful is actually like when we're computing. The reason this is useful is because we can define value in terms of Q value. And in particular, we can say that value of a state is just the max over all the Q values. So basically what you do is you simulate taking an action and choose the best one. Sorry, I really can't tell how, if my internet is really bad. Is it troubling people? Type in the chat. Okay, cool. Maybe it's just on my end. All right. The last thing is policies. So what we really care about with MDPs is like, what do you do? And in order to figure out what to do, we basically, instead of taking a max over the actions, we can take an argmax. So we'll say which action gives me the best Q value. Yeah, maybe if I turn off my camera. Sure, let me do that. Thanks. Okay, so these are like all the things we care about. But now we're going to talk about how to solve MDPs. So in order to solve MDPs, we use these like this cool set of equations called the Bellman equations. I just have like one here. And it's basically defining value, the optimal value. And it says that the optimal value of a state is the max over all the actions. So sort of choosing the best action to take of how much value you get from that action. And the value that you get after taking that action is just the reward that you get from transitioning to state S prime after taking action A, plus whatever value you get like after you've taken that action. So basically, like, you'll start in some state, you'll take some action, and you'll land in some other state S prime, but your life doesn't end after that. Like from state S prime, you still keep acting. So that's why we have this value of S prime term in there. So this is how we can sort of like recursively define value. And you'll notice that this is just an expanded form of this max of Q value that I wrote here. Is the symbol next to the V star a gamma or an alpha? That's a gamma. Sorry, that's a discount. Okay, so this brings us to like our first strategy of solving MDPs, and that is value iteration. So with value iteration, the key question that we're asking is, what if you only had k time steps to live? So if k was 0, then you only have 0 time steps to live. Then for every state, the optimal value is just 0, because you really can't do anything. You can't gain any value. Then we say, okay, the value when you have k plus 1 time steps left is just the value of you taking one action and then acting as if you have k time steps left. That's the big idea with value iteration. All right. And the other way we solve MDPs is using policy iteration. And in order to introduce that, I have to go on a slight tangent and introduce this thing called policy extraction. And here the question we're asking is like, once we know the values, how do we actually figure out what to do, right? Like if someone gives you the values of an MDP, like that doesn't really help you much. You want to figure out what actions you want to take. And the way we do that is we do this sort of like depth one expect to max. And how it works is you basically say, okay, the optimal policy is the argmax over all the actions. Sorry, does someone mind muting? Not sure who's talking. I'm going to mute people. Thanks. All right. So yeah, we take the argmax over all the actions of the Q values. That tells us like which action is the best, which action gives us the best Q value. And so we just expand that out and we say argmax over A of the formula that we derived for Q value. So we can use this like sort of tangent thing and apply it to this strategy called policy iteration. The question that we're asking here is, do we need precisely the optimal values to figure out what to do? Or can we do with values that are like pretty good? So you might have noticed in lecture when you were doing like the grid world example, like you knew like what the optimal policy was much before the values converged, right? Like even after like many iterations, the values were like changing by like very little. And so value iteration hadn't converged. So we say, okay, let me just try to learn the policy sort of directly. And so the way this works is first you define some initial policy, and this can be good, this can be bad, but like it's better if it's closer to the optimal policy. Then you say, okay, use this policy to compute values for states. So you say the value of a state under this policy pi is going to be just a regular value formula, except instead of maxing over all the actions, we're going to say take the action that this policy pi gives you. So pi of s. What does pi tell you to do when you're at state s? And so that gets rid of this max term that we usually have. And it allows us to do this sort of value computation much faster. So there's two ways you can do this. The one you might have talked about in lecture is going to be just do like a value iteration, like a regular value iteration, but just use this formula. So without the max. The other way is that now that you have like, you don't have the max, this is basically like a system of equations. So you can say for each state, you can say like value of S1 is equal to something, value of S2 is equal to something, and you can sort of just solve this system of equations as well. But I don't believe you talk about that too much in lecture. And finally, what we do is we use these new values that we've computed that are slightly better than like our original estimates, and we extract a policy. So that's this part, policy extraction. That's when we run policy extraction. And we say, what is the best policy if these were the values? And then we sort of repeat and we say, okay, use those values, use that policy to compute new values. And then so on. And at some point, your policy at iteration I+1 is the same as the policy at iteration I. And that's sort of when you know you've converged and you can stop. Okay, yeah, that was very fast. Any high-level questions? I don't want to get too much into detail. I want to get to the worksheet. But yeah, high-level questions about policy iteration, value iteration, or MDPs.
I have a couple questions.
Go ahead.
Sorry, I get my mic. Okay. Firstly, so to do policy extraction, you just need like the convergent values from value iteration, right? You just need that like last row at the last time step when it converges.
Yeah.
And then you can just like do another one using this rule for policy extraction to get the argmax. And it'll be the same, like the next row will be the same values, right? So you're just doing it for the sake of getting the actions.
Yeah, that's correct. You're only doing it for the sake of getting actions. So that's why we like say, okay, instead of doing this computation, just store Q values directly.
Okay. Okay, yeah, that makes sense. And then for policy improvement and policy iteration, why does that guarantee convergence for like like why is it that like we know that it's optimal when pi I plus 1 is equal to pi I?
Yeah. So, well, for one thing, the first part of this is like, okay, we know that the policy is no longer going to change. And the reason we know that the policy is no longer going to change is because the values for the states that the policy gives you is going to be the same. And so this step is going to give you the same extraction. But to your other question about like why we know this is optimal, um, I don't know if I can provide any good intuition for that right now, but I will send you a link uh, to this textbook if you want to read it, and we can talk about it at the end of this review session if you'd like.
Okay, thank you.
It's in the chat. Yeah. All right. I think we should start the worksheet, but we can definitely tackle questions as they come. And yeah, feel free to interrupt me. So the first question that we're doing is with Pac-Man. Actually, most of the questions we do are just with Pac-Man. And Pac-Man is this in this sort of grid, and he has the regular 4 actions of north, south, east, and west. There's a reward of 1 point when you eat a dot. So for example, the reward of C, south, F, which means start in C, take action south, and get to F is 1. And the game also ends when the dot is eaten. So the first part of this is basically we're considering this grid, and the discount factor is 0.5. We want to figure out what the optimal policy is for each state. So take a minute and try to figure that out. Okay, anyone want to tell me what the optimal policy is from each state? We can start simpler. What's the optimal policy from state C?
South?
Sorry, did you say south?
Yeah.
Okay, yeah, that makes sense. From C, we just go south because we want to get the food, right? And we can say the same thing for E, because that's symmetrical. What about for the rest of them?
For D, we go east.
Okay. Yeah, so for D, we go east. For A, we can go right or down. And for B, we can go right or down. And basically what's happening here is we're in every step, we want to get 1 step closer to the goal. And the reason this is important is because we have this like discount factor, which means that we want to get to the goal or like the pellet as fast as possible. So if we take any longer than we're like supposed to, then that would give us less of a reward because the like one reward of 1 would be discounted more. So yeah, from A, you can go down or right because either way, you're 1 step closer to the goal. Okay, cool. Yeah, that is the optimal policy. We're now going to figure out what the optimal value is for the state A using this discount factor of 0.5. So once again, you can take a minute to do it. And when someone has an answer, feel free to type it in chat or explain to me how you did it. So for this question, it helps to view value as like the expected sum of rewards. And so what we can say is basically the value is some discount times the value of your step one, then then discount squared times like reward two, plus discount cubed times reward four, and so on. So it's sort of like sum of rewards. So can anyone tell me the expression that we would use for V star of A?
Point 0.5 plus 0.5 squared plus 0.5.
Sorry, I lost you a bit. Do you mind repeating? What is there anything being multiplied by the 0.5s?
Oh, the transition probability.
So in this case, we're deterministic, but what we do need to multiply is the rewards. So
So you can 0.5 times 0 plus 0.5 squared times 0 plus 0.5 to the third power times 1 because you can only get a reward of 1 in 3 steps.
exactly, yeah. So that's correct, and so that's or I think it's 0.5 squared times 1 because you get the reward when you're transitioning from C to F. But I seem to have lost internet again, unfortunately. Sorry for the inconvenience. Let me join the meeting again.
But isn't the reward from like the thing is 0.5 square when you go from B to C?
Let me see. Okay, it is back. So yeah, so what we do is we say we go from A to B, and that gives us reward 0. Then we go from B to C, and that gives us gamma times reward 1. And then the next one, which is going from C to F, that gives us gamma squared times 1. So you have to be careful about like your initial reward is not discounted, right? If you look at like how we defined value, let's see where it is.
Yeah, that makes sense.
Reward, and then the rest of it is discounted. So yeah, that's what's going to end up happening. We're going to get 0.5 squared times 1, which is 0.25. Sorry, just waiting for the screen to update. I'm not sure if the screen updated, but the next question is using value iteration with initializing all of the values at 0. For which iteration will this value of A converge? I think what I'm going to do is just send you a link to the worksheet so you can look at it on your own and try to bear with my internet, which is. Here's the link. Yeah, sorry about the inconvenience. But yeah, just try to figure out how many iterations it takes for value iteration to converge at state A. Does anyone have any ideas? Okay, so well, we can basically consider like which state's values will converge after one iteration. So can someone tell me which state's values would converge after one iteration? Yeah, Sierra says E and C. Yeah, that's right. So in one iteration, C can basically say my value is going to be the reward that I get from transitioning to F. And that's it, right? And that's the optimal value because C just got to F. And now the value of C has been like, it's correct now. So let me just write check mark. From there, we can do a similar thing. Now that there's values of C and E, their neighbors, B and D, can use those values to get their optimal values. So B can say, okay, I get 0 reward, but then I get discount times the value of C. And D can say, I get 0 reward from transitioning, but then I get discount times the value of E. And then finally, in the last iteration, A can say, okay, I get 0 reward from going to A to B, and then discount times value of B. So it takes 3 iterations. And you can see that in another way. We can take a look at the solutions where we have this value iteration table. So you'll notice all the values get initialized at 0, and then C and E now have their optimal value. Then B, C, D, and E have their optimal values, and then everything has their optimal values in iteration 3. All right, any questions so far? Okay, feel free to interrupt me if I do something that you don't agree with. Okay, so what we're gonna do now is consider like this new Pac-Man level where they have these cherries. And so basically landing on a grid with a cherry gives you 5 points. And the dot is still there, it's worth 1 point, and the game only ends when the dot is eaten. So that hasn't changed. So what we're gonna figure out is with no discount and a living reward of -1, what's the optimal policy for the states in this level state space? And so the first question I'm gonna ask you all is like, what is the state space? Can we use the same state space as before? Thoughts? In particular, look at the fact that the cherries disappear after you eat them. Yeah, so Mark says the position of the Pac-Man, as well as whether D was eaten and whether F was eaten. The reason this is important is because we had this like property in MDPs, which is like the Markov property, right? So they're Markov decision processes. And that basically tells us that the future is independent of the past given the present. And another way to sort of express that is say, okay, your transition function, SAS prime, and your reward function, SAS prime, never change. Whereas if our original state space was just A, B, C, D, E, F, then after you eat the cherry, the reward from C to D would be different. So if you've already eaten the cherry. So we need to keep track of this extra information. And so what that makes it so that we actually have 24 states instead of 6 states. Because you basically have the 6 regular ones, and for each of those you have 4 possibilities: true, 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 false, 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 true. And so I'm going to bring this up. And instead of figuring out the values for all 24 states, I've written 3 states here that you can try to compute the values, the optimal policy for. So just as an example, the first one reads, what's the optimal policy from A if there is a cherry at D and a cherry at F still remaining? So yeah, once again, you can take a minute or two and try to figure that out. Okay, no worries if you didn't get to all of them, but does someone have an idea for the first one? Okay, I can actually just talk through them. I know this is a bigger section than usual, and also we're recording it, but that's okay. So from A, you have to basically decide, should I go right or should I go down? And in this case, we actually don't really need to go do any computation, because usually you'd have to like figure out, okay, like either I eat like one cherry or I eat both the cherries, or I just go straight to the dot. But in this case, taking either of these steps is going to get you one step closer to the cherry, and taking a step to the right is going to get you to the dot. So we can at least say that one optimal policy from A is to go right. The other one that people have mentioned in the chat is that it also works out that you can go down, because it is optimal to eat both the cherries. And the way we can figure that out is say, okay, there's a living reward of -1. How long does it take you to eat both the cherries? Well, it takes you 1 step, 2 step, 3 step, 4 step, 5 step, 6 step, 7 step. So -7 is your living, and then you get plus 11. You get 5 for each of the cherries, and then 1 for the dot. And so this is, if I did the computation right, this is definitely better than at least eating 1 dot, in which you just get -1 for traveling to the dot and 1 for eating the dot, which is 0. Feel free to correct me if I made a math mistake, though. All right, what about the optimal thing to do from D when there is a cherry at F? We can use sort of the same logic here, that it does make sense to go to F and eat the cherry. And so we're going to use we're not going to redo the computation, but we're going to go right and eat the cherry. Nuja says, but if we go right, the game ends, right? The game ends, that's correct. Oh, yeah, sorry, that is my mistake. We can't go right because the game would end. Thanks. Okay, and the last one is E, F, F. So basically, there are no more cherries and we're at E. Then you want to get out as soon as possible because there's a negative living reward, so you just go left. Okay, so using sort of the intuition that we built in part 1, we're asked the question, with no discount, what's the range of living rewards such that Pac-Man eats exactly 1 cherry when starting at position A? So in order to solve this question, you can think about like what would make Pac-Man go straight to the exit, what would make Pac-Man only eat 1 cherry, and what would make Pac-Man eat 2 cherries. And between the 0 and the 2 is going to be your 1 cherry. So try to write a couple inequalities to come up with this.
Oh, I had a question. In the first part, why did we say that? I mean, the game ending is just like we end up with a lower reward, right? Is that why that's not an optimal policy?
Yeah, so originally I had thought that, oh, like you could go right and then go down and eat the cherry, but the game ends, so that's not valid. And yeah, that's a lower reward, what you said
Okay.
before. Any ideas for one inequality that I could write? Okay, let me reason through it. So what we said before was that eating both of the cherries means you end up taking 7 steps, right? 1, 2, 3, 4, 5, 6, 7. And the amount of points that you get are going to be 7 times the living reward, let's call it X, and then plus 5 plus 5 plus 1. Okay, that's one option. So this is both cherries. For one cherry, we say the reward that you're going to get is going to be 1, 2, 3 total steps, which is 3 times the living reward, plus 5 plus 1, 1 cherry and 1 dot. Finally, for no cherries, the reward that you're going to get is 1 times the living reward plus 1. So what we want here is we want 1 to be better than both of these options. So we want to say 3x plus 6 has to be greater than 7x plus 11. And we want to say 3x plus 6 has to be greater than x plus 1. And so if you solve both of these inequalities, you'll get that x is greater than negative 2.5 and x is less than negative 1.25. So the idea there is that if the living reward is too negative, then you want to go straight to the dot. And if it's not that negative, then you have enough time to just eat both dots. And then if it's somewhere in the middle, then it's optimal to eat 1 dot. Any questions about this? Okay, great. Let's move on to question 2, strange MDPs. So this is another MDP, and you can imagine that you have like Pac-Man or someone in here. You have these 4 states, A, B, C, and D. And at state D, you can only exit. From any other state, going to a non-exit state gives you a reward of 1. And from D, exiting gives you a reward of X. So the first thing we're going to do is assume we have a discount factor of 1/2 and express the following only in terms of X. So we're going to basically find the optimal values for these 4 states. This one is a bit tricky, so definitely take like at least 2 minutes to do this. And consider that you can use a max in your answer. But still keep your numbers to just, or variables to just X. So let's start with just the optimal value of D. Can someone tell me the optimal value of D? X. Yeah, that's right. So from D, you only have one action. So you take that action, get the reward of X, and then you're in a terminal state. So you know no more future rewards. Perfect. Anyone have ideas for really any of the other ones? X over 2 plus 1 for which one? For C. X over 2 plus 1. Okay. How did you reason about that?
I thought because the discount factor was 1/2,
Mhm.
so I took 1/2 of the V star of D, and then plus the reward that I can get from C.
That makes sense. So yeah, so what you did was you go to D, you get reward 1, and then you get discount times V star of D. Perfect. There is a catch. Is going to D always the best option? So it turns out that it's not always the best option. The other option that you have is you could just sort of oscillate back and forth between B and C, or just keep getting this reward of 1, right? If X is small enough, then you might prefer that. So what reward would you get if you just sort of oscillate back and forth here forever? Well, initially you'll get 1. And then in the next time step, you'll get discount 0.5 times 1. And then you'll get discount 0.25 times 1, and so on. So this is like this infinite series or geometric series. And it's just 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 and so on. And this is just like, this goes to 2. And the reason why is because you can imagine like a circle. You take 1/2, then you take 1/4, 1/8, 1/16, and eventually you fill up the circle. You approach the circle. So this part goes to 1, and this part is 1. So that's 2. And so what we can say is that the value here is the max between these two options based on whatever value of X, since we don't know what X is. And side note, in general, you can get the sum for these by doing 1 over 1 minus the ratio. In this case, the ratio is 1/2 because every term is 1/2 times the other one. Can we leave it as 1 plus 0.5 value of B? I'm going to say no. I think not. Since we're only leaving it in terms of X. Okay, so now that we have V star of C, we can also use this reasoning to get the other ones. So you'll notice that A is basically symmetric to C. It's just right across. So it's going to end up having the same value. And you can just reason through the same way. You can say get a reward of 1 and then get a reward of 1/2 plus X times X. Or just do this infinite oscillation thing. And for B, you say, okay, it's the max of your reward of 1. So if you either try to exit, so go here and here, plus 1/2. Oh, sorry, for B. That's my bad. So for B, you go, say, down, and then plus 1/2 times 1 plus 1/2 times X squared times X. And the max of that would 2. And another way to write this, just to provide another perspective, is 1 plus the discount of the value of C, which is 1/2 X plus 1. Or in the other order, 1 plus 0.5X. And so this 0.5 gets propagated, and this becomes a 0.25, which is what we've done here. Okay, any questions about A? Okay, let's try B. It's kind of challenging, but let's try to work through it. So we're saying that now any non-exit action will only be successful with probability 1/2. Otherwise, the agent's going to stay in the same state and they're going to get reward 0. The exit action is still deterministic and that'll always succeed. And we have our discount factor 1/2. So the question we're being asked is for which value of x does the Q value, optimal Q value of taking action down from A equal the optimal Q value of taking action right from A. So I'm going to go to the next page here. We need some space for this one. But yeah, try to think about this for like a minute or so, and I'll give some more hints after that, and we'll work through it together. So my first hint is, what is V star of A in terms of the Q values? Any ideas? So it turns out that from state A, there's only 2 actions, right? There's down and there's right. And we know that the Q values of both of those actions are equal. So V star of A is equal to Q star of A comma down, and that's equal to Q star of A comma right. So that makes our life easier. Anything we're writing where we're writing QA down, we can also use QA right, and so on. So let's compute this. Let's compute Q star of A comma down, which is also equal to V star of A. So we'll say that from A, there's a 0.5 probability of you successfully going down, right? So there's a 0.5 probability of you getting the reward 1, and then you exiting from D, because exiting is deterministic, and that's the best action to do from there. And remember, that's discounted. The other option, which also happens with 0.5 probability, is you just stay in A. And this is where we can use the property where the optimal value of A is the same as these Q values. So we can just say 0.5 times just the value of staying in A. And so you can rearrange this and just say, oh, sorry, I think 0.5 times a reward of 0 for your action failing plus a discount times the value of staying in A. Be careful with the discount. I always forget it. So then we can rearrange this and just write 0.75 times V star of A is equal to 0.5 plus 0.25x. I think that looks right. And we can do the same thing for the other Q value. So we can say Q star of A comma right is equal to V star of A, but in particular, it's 0.5 times you successfully going right, which gives you a reward of 1, plus the value, optimal value of B times a discount. Because B is where you landed. Otherwise, we have the same term, 0.5 times 0 plus 0.5 times the value of a, because you're just stuck in a. So now you might be thinking, like, what is the value of b, right? Do we even know what that is? We don't really yet. So the next thing, the last thing we need to do is be able to write the value of b. And the cool insight there is that the value that b is also in a symmetric position here. So if we go from b to a, or if we go from b to c, that gives us sort of the same result, because a positioned to the exit and c positioned to the exit is like in the same way. So we can say that from b, we can just say that going left will give us the optimal value. And so we can just say v star of b is equal to q star of b comma left. And that's going to be like 0.5 times successfully going left, so getting the reward, and then discount times value of a. And 0.5 times failing and getting discount times value of b from then on. And you can once again rearrange this to be v star of b is equal to 2/3 plus 1/3 v star a. And I definitely skipped a math step there. Finally, you can plug this in right here. And then you will be able to solve this system of equations about v of a and x, because you have two variables and two equations. I guess I won't solve it now because I'm running out of space, but I did it right below, if anyone is interested and got that far. It was kind of a long algebra process. But yeah, this will be there in the answer key as well, and we end up getting that x is equal to 1. Right, I think we are out of time. If anyone has additional questions, feel free to stick around, and notice that there is a question 3 on the worksheet that you can also try. It's a pretty good question. Thanks for coming.
Akshat,
What's up?
will the solutions for these exercises be posted?
Yes, they will. I'm sure at least on Tuesday they'll be posted.
All right, thank you so much.
I will post my work, so there's not too much, but yeah.
I had one question. Why did you only choose Q's, the optimal value of Q of B comma left?
Yeah,
What-
so good question. If you look at this grid that we have, going B left is the same as going B down. Do you see why?
Yeah, because A is the same. I mean, A and C are both same distance from the exit.
Yeah, they're basically like the same state. And so since you only have two choices, the best of these choices is either of them. So to make, since we wanted stuff in terms of value of A, we made the choice to go left.
Oh yeah, and we're talking about the optimal value here. So yeah, okay, that makes sense. Thank you.
Cool.
I have a question, just like going back to the like first question, like part A.
Mhm.
Like when you wrote like the V of S is like the sum of the discount to the power of I times the reward of I. Is that like, did you get that formula because there's no living reward? Like, would it be different if there was a living reward? I just wanted to like make sure my
Mhm.
understanding of that was correct.
Yeah, so this is sort of like a hand wavy formula. It's not like too legit, but
Mhm.
the living reward would just be factored into your R of I. So your R of I would always be like reward from transition plus living reward.
Mhm.
So like you can imagine that like your reward function is always going to give you like the living reward plus like whatever you get from the transition.
Okay. Yeah, that makes sense.
Cool.
So, Akshay, I had a question as well.
Mhm.
So, in question 2, why do we know that V star A is equal to Q star A down, which is also equal to Q star A, right?
Yeah.
So like just like the first line.
So from A, we only have these two choices, to go right or to go down. If we say that either going right or going down gives us the same value, then both actions are just as good. And so either of them can be treated as the optimal action.
Okay. Okay. Yeah, that makes sense.
Function that we made here. Q star of A is equal to Q star of A, down is equal to Q star of A, right?
Got it. Cool. Thank you.
Yep. Okay, hopefully my internet isn't broken anymore. Yeah. Any other questions? Okay, I'll stop the recording then.